Hi everybody, welcome back to part 4 of chapter 27, and this should be the last video for this chapter. And in this chapter what we want to do is look at how having a combination of resistors and capacitors in the same circuit will affect not only the behavior of the circuit but also the math that goes into this. And actually I'm going to put a switch into this diagram. And what the switch does is it just allows us to have alternate paths for the current to follow. And so this switch here can swing back and forth to either connecting the battery, which we are now labeling as an EMF, to the resistor capacitor combination, in which case the switch would bridge the gap here, and this portion would remain open. Or we can flip the switch down, in which case the only closed path would be what is made of the resistor and the capacitor, and the bridge between the circuit and the battery would remain open. Now we do have to have a closed path in order for any of our Kirchoff's law expressions to work. And so that means the switch either needs to be connected to the battery or it has to be down in the other position. Otherwise, right now, there are no closed paths available in the circuit. So I'm going to go ahead and start us off by having the switch connected to the battery. And now we can see a closed path that includes the battery, the resistor, and the capacitor. This portion right here is not contributing to anything because this is not part of any closed loop. So we don't need to worry about this right now. And our battery, our resistor, and our capacitor will all have certain values associated with them. If we need to, we can put some values in right now, but I don't plan on using these for a while yet. We'll say 50 ohms and 200 microfarads for the capacitor. So how is this circuit going to behave? If we start by having the switch open, in this scenario, we're going to assume that the capacitor currently does not have any charge on it. So when we close the switch, when we provide this bridge for charge to start moving, charge is going to come out of the battery. It's going to pass through the resistor, and it will start building up charge on the plates of the capacitor. And likewise, we will see negative charges start building up on the bottom plate of the capacitor. But this can only last for so long. Eventually, this capacitor is going to reach a maximum charge based on the potential across its plates and based on the potential of the battery. While the charge is moving from the battery to the capacitor, it has to pass through the resistor. As that is happening, we refer to that as current. So all the while, we have charge that is building up on the capacitor plate, and this amount of charge is changing with respect to time. So this charge value will be a time-dependent function. As more and more charge builds up on the capacitor plate, any subsequent charge that tries to deposit onto that capacitor plate is going to be repelled. And so these charges are going to slow down. As those charges slow down, well, that means that the flow of charge in the circuit is going to slow down. And that means that our current is now also a time-dependent function. And this is something that we've not yet encountered with the other circuit diagrams, is having a changing current value. We've always been using uniform current. And so we need to put some math to this, and to help us out, we're going to consider some extreme situations. The first extreme that we'll consider is how much charge was on the capacitor when time equals 0. So how much charge was on the capacitor before we connected the battery to the circuit? And, well, we already know that it was 0. How much charge will end up on the capacitor after it is fully charged? And, well, we don't have a number for that yet, but we could call it Q max, whatever the maximum charge is that will end up on that capacitor. Question is, how long will that take for the capacitor to reach full charge? And that we don't know for sure, but let's just say we have enough time on our hands that we can wait as long as it takes for this capacitor to reach its maximum charge, and if that means we have to wait forever, so be it. So if we let the clock go forever, we will eventually reach a maximum charge on our capacitor. Now we will come back and fix this a little later. We're not actually going to keep it at infinity, but this, as I said, was going to be one of the extreme values. The other thing we need to figure out is what are the current values going to be at these initial and infinite time values. Well, we'll start at infinity. If we let this circuit go long enough, eventually we're going to reach a maximum charge on our capacitor, and that means there's no more room for any more charge. That means that we can't move any more charge through the circuit, and the current will go to 0. So if there's a 0 current, does that imply that there's a maximum current? And it does. The maximum current will occur when the capacitor is empty. If the capacitor is empty, then there won't be any charges on the plate to repel incoming charges, and we should see a maximum value of current at time equals 0. Now these are things that we can argue. They should make sense, but can we prove them in the mathematics? And the way we're going to do that is to use Kirchoff's law on this circuit. First step of Kirchoff's law says you need to pick a starting point on your circuit. We have a closed path that involves the battery, the resistor, and the capacitor. I will just start right here at this random point, VA. I will choose to travel around the circuit in a clockwise direction. In other words, I'll go with the current. We'll start with our summation. Whoops, that's not equals. We start at VA. We pass through the resistor going with our current. Now, our current may be time dependent, but that doesn't mean that Ohm's law is going to change. All this says is that if I have a time dependent current, then the potential across that resistor is going to become time dependent as well. So we have the current that is going through the resistor, I sub t, times the resistance. We are going with the current, so that is a drop in potential. Then we get to the capacitor. Now, the capacitor has this gap in between the plates. Whether that gap is empty or if there's some kind of dielectric material in there, the point is that the charge cannot cross that gap. And so we don't have current that we can use going across that capacitor. But that's okay, because we already have an expression from chapter 25 that says that the potential across a capacitor can be measured as the charge to capacitance ratio. Just like the current, the charge is time dependent, which means that the potential across the capacitor is going to be time dependent. As we cross the capacitor, we emerge on the negative plate, and that tells us that there has been a drop in potential. And we're going to use the Q over C ratio to represent the potential for the capacitor. Once we get past the capacitor, then we travel along and we have to pass over the battery. Emerging on the positive side of the battery, that will be an increase in potential. And now we're back to our starting point, VA. We can factor those out. VA was just there as a placeholder. And Kirchoff's law says that the sum of all the potentials has to go to 0. Now, this is kind of an interesting system, because at all times, this summation has to equal 0. But as time goes by, the amount of charge that we have on the capacitor plates continues to increase, and the rate at which charge is flowing through continues to decrease. So how do we get a solution to an equation that has ever-changing values? And for that, we're going to need a little bit of help from the calculus. Since we have ever-changing values, these are changing rates. That is what calculus is specifically designed to handle. But we're going to run into a problem here, because we have two unknowns and only one equation. We're going to have functions for the changing charge and the changing current, and I can't solve for two unknowns if I only have one equation. Except that current, by definition, is supposed to be the change in charge with respect to time. So what if we were to replace that current term with dq dt? Well, now we get something that looks like this. And I'm going to factor a -1 out of everything, just because I don't like having so many negatives. And what we have just produced here is a first-order differential equation. Now, some of you might be thinking, oh, I haven't taken diff yet. Should I have taken diff? Well, diff is not a prerequisite for this course. You will run into situations like this when you take diff, but for our purposes, what we really need is just the solution to this expression. The steps involved in getting from here to the solution, those will be covered when you take differential equations. If you've already taken differential equations, you might be thinking about some of the different methods that you might try for finding a solution to this. But for right now, we'll just say that there's some math magic that goes on, and we're going to drop down to the solution. I will make a couple of comments on this when, oops, I forgot my R term there. Need to bring that in. When it comes to finding a solution for this, you are taking a function for your charge. So whatever QT is, you're dividing it by a coefficient here, the value of your capacitor. That's just a coefficient. Your EMF potential, that's just a numerical value. That's a fixed constant. And so the only way that we're going to be able to get all of this to equal 0 is if everything is of like terms. So what do we mean by like terms? Well, as you know, you can't add x and y directly together, but you can add x and x. Well, if we're going to add all three of these terms together and get 0, that means that they have to be like terms of one another. And that means that the original function of q and its derivative, dq dt, are like terms. And the only thing that they differ by in terms of their values are the coefficients of capacitance and resistance. This is really important because now we have a better idea as to what kind of function we need as the solution of Q. Can you think of any function that is a scalar multiple of itself? And if you go through a lot of different examples that we've had in calculus, maybe we try x squared, but the derivative of x squared is 2x. Those are not scalar multiples of each other. Those are not like terms. Maybe you try a trig function. Well, sine and cosine are not like terms. Then you try maybe exponential, and the derivative of exponential is e to the x. And you're like, oh, that works. So what if you had e to the ax? What would you get for a derivative? Well, you would get e to the ax. And that's exactly what we need in order for these two terms to combine in such a way that they're going to cancel out and make 0. So that information combined with what we have from Kirchoff's law, this is basically the first week or two of differential equation is a trial and error process and seeing what kind of functions will actually work in the differential equations that you make. But we want to jump ahead to the actual solution for this equation. And let's clean this up a little bit. So the solution to this equation is Q of t equals CE 1 minus e to the negative t over RC. So that is an exponential function. It involves the values of the capacitance, the EMF, and the resistance of the resistor. And just in case we were wondering, is this actually the solution to that equation? Well, plug it in. Take Q of t and plug it into this equation. We will need the derivative of Q. We can do that without too much hassle. CE is a constant that's going to come along for the ride. The derivative of 1 is 0. Then right here I have to take the derivative of negative e to the negative t over RC. Now we don't have e to the x, we have e to the t, but if we were to equate this to e to the at, we do have that minus sign out front, but what would a equal? Well, it would equal all this other stuff. So a is equal to a negative 1 over RC, and the derivative of this would be, we would have the negative out front, the a drops down, and then we have e to the at. So what we get is negative a. There's a, but there's a negative out front, so now it's positive 1 over RC, e to the at. So e to the at. Or the capacitance values are going to cancel out in the front. We get e over r, e to the negative t over RC. So that's the derivative. We need to put all of this together in that equation. So we need dq times r. Here's all of dq. And if we multiply that by r, well, we just get e to the negative t over RC. We have to add that to Q divided by C. Here's Q. And if we divide that by C, we're just going to get E 1 minus e to the negative t over RC. We have the minus e. And all that should equal 0. So, moment of truth. Does everything equal 0? Right here we have e to the negative t over RC, plus here's e negative e to the negative t over RC. So those are going to cancel each other out. And then we have just e minus e. So yeah, that equals 0, which means that that is in fact the solution for Q. And this, the derivative of Q with respect to t, is the current. And so we actually get a free expression out of this. We have a time-dependent function for the charge that is on the capacitor at any given time, hence the time dependency of our function here. And we have a time-dependent function for the current that is running through the circuit at any given time. So what does all this mean for us? Well, let's take those equations that we just made, and I'm going to clean up the screen here. We're done with all of this. So these two equations that we just made, do these match up to the extremes that we discussed earlier? We said that at time 0 there should be no charge on the capacitor plate. Okay, so Here's the charge expression. If we let time go to 0, what happens? Well, we get e to the 0, and anything to the 0th power is 1, but that means we have 1 minus 1, which is 0, so yep, that is working out. That matches up. If we let our time go to infinity, that is when we should achieve a maximum charge. Okay. If we let time go to infinity, we get e to the negative infinity, which would essentially be 0. But we still have the 1 out here, 1 times CE, so that's the maximum charge. The max charge that we will expect on that capacitor is equal to CE. At infinity, we expect the current to be 0. So we'll let time go to infinity with our current function. E to the negative infinity, that goes to 0, so the whole thing goes to 0, and yep, that checks out as well. But then we said that the maximum current should occur when time is 0. Okay, when time is 0, let's see here. Oops, I made a slight mistake here. The current function has the R still in it. So, sorry about that. If we let time go to 0, we have e to the 0, which is 1, and so all that's left is that our maximum current at time t equals 0 is equal to E over R. Okay. Well, now that we have these equations, we can effectively answer just about anything for any time. But I'm kind of curious now, if we have those values for the battery and the resistor and the capacitor, what contributions are those going to make to the charge or the current as time goes by? Well, the first thing that we need to look at is the product of the resistance value and the capacitance value. And this is basically where we get the title for this section of the chapter, which is RC circuits. In both of our time-dependent expressions, we end up with e to the negative t over RC. And RC is given the name of tau. And this is called the time constant for the circuit. The larger the ratio of RC, the more it's going to affect the time dependency of this function. In fact, whenever you have anything raised to a power, that power is supposed to be unitless. But we already know time has units of seconds, R has units of ohms, capacitance has units of farads. Well, if this is in fact going to be a time constant, RC will have the units of seconds. That's the only way that we can take a ratio of time and something else and get a unitless compound. So tau is equal to RC, and tau is going to have units of seconds, just like any other time would. But considering that rate, that product there of RC, let's take a look at our circuit again. We have our capacitor We have our resistor. Everything's connected to a battery right now. And we're going to go back to the water analogy. We're going to pretend that our battery is a source of water. And we want to use that water to fill a container of some kind. So our container is going to be the capacitor. Well, our capacitor could be really small. It could be something like a cup, or it could be a swimming pool. Our resistor is going to be the hose that we use to fill up one of these objects. And the resistor, it could be a garden hose or it could be a fire hose. So in these cases, we have a garden hose, which is not really going to allow for a whole lot of water to flow. And that would be the equivalent of having a very high resistance to the flow of water. Whereas a fire hose would allow a lot of water through, or a low resistance. The cup would be a fairly small container, and that would relate to a small capacitance value, whereas the swimming pool would have a very large capacity and a very large capacitance. So now we consider the combination. If you were to take a garden hose and attempt to fill a pool with it, well, so you have a large resistance value and a large capacitance value. How much time is it going to take you to fill a swimming pool with a garden hose? Well, it's going to take you a long time. As a result, by having a very large tau value, it's going to take you a long time to accomplish what you're doing. In this case, with a very large tau value, it's going to take us a long time to reach the maximum charge for this capacitor. On the other hand, what if you wanted to fill just a regular cup, but you use a garden hose to do that? Or, not a garden hose, a fire hose. So now you have something with very low resistance and very low capacity. That fire hose is going to fill that cup like almost instantly. Or the product of the two, having a low resistance and a low capacitance, will result in a low time constant. And with a low time constant, you're going to be able to achieve filling up that capacitor very quickly. And that should make sense with the analogy here. If you have a very small capacitor, there's not much room for it to hold charge. And if you're using a wire or a resistor that has very low resistance, well, that current is going to come through very fast and fill up that capacitor very fast. The garden hose and the pool analogy, that's obviously on the opposite end of the spectrum there in terms of the example, but then what if you were trying to fill your cup with a garden hose? So now you've got a high resistance and a low capacitance value. Well, that means that you would end up with a time constant that's somewhere in the middle, kind of medium range in terms of time. Or you could try filling the pool with the fire hose. In that case, you would have a very low resistance, but a high capacitance. Again, you would end up with a tau value that's kind of in the middle somewhere. So that tau value, the larger the tau value, the longer it's going to take to do whatever it is that you're doing here. In this case, we're trying to charge up the capacitor. But I'm really interested now. How long is it actually going to take for this capacitor to reach maximum charge? We have an equation right in front of us that says the charge at any given time equals CE 1 minus e to the negative t over RC. Well, I want to know how long that's going to take. And I already know what the maximum charge should be. So let's set this equal to CE. I want to achieve the maximum charge. So I've got the maximum charge. I've set that equal to the time-dependent function. And, well, CE cancels with CE. I'm left with 1 equals 1 minus e to the negative t over RC. I subtract 1 from each side. I get 0 equals, well, that's not good. Because now I have that second term equal to 0. And if I try to solve for t, the only way to do that is I have to bring t outside of the powers place. And the only way that I can do that is by applying a natural log to each side of the expression. The reason I want natural log is because natural log and e are natural enemies, and they will eliminate each other. And so now we have natural log of 0 equals negative, negative, which is positive, and then we could multiply RC over. Except if you try plugging in natural log of 0, you're going to get undefined. Well, could we use the current expression to get around that? Because we know that when the current goes to 0, there has to be a time value associated with that, and could we solve for that time? Well, if we let the current equal 0, then E and R can factor out, and we're right back to the same situation where we end up with an undefined time. There is a way to get around this, I promise you. The problem that we had was that we got a little too ambitious. We tried to go for 100% of that maximum charge. And going for that 100% was the reason why we weren't able to solve for the time. What if, instead of trying to go for 100% of the charge, what if we tried 99.9% of the maximum? If that were the case, then we could say that 0.99 of the maximum CE, we would set that equal to our time-dependent equation. And once we do that, we end up with 0.999 equals 1 minus e to the negative t over RC. I can subtract 1 from each side, and I get a negative 0.001 equals negative e to the negative t over RC. I can cancel out the minus signs on each side. I can then apply a natural log to each side. Again, I'm doing that to eliminate the exponential. Natural log and exponential cancel each other out. And what I'm left with, once I remove the exponential, the t over RC term now drops down, and we can move that around algebraically. I will multiply each side by RC, and that equals a negative t, but I can bring the negative side over and I get a t there. Now, looking at that, you might say, well, that's not right. We can't have a negative time. But we haven't evaluated things yet. If you remember your natural logarithms, if you try to take the natural log of anything that is smaller than 1, you get a negative outcome. So our natural log of 0.001 gives us a negative 6.91. And then we have to bring in the values of RC, or tau in this case. Well, let's go back up here and see what our tau value is for this circuit. And way up here, there were the values. So tau equals RC. We have 50 ohms and 200 microfarads. Our 200 times 50 is 10,000. We have micro, and if we remember, we said time constant was measured in seconds, so we have 10,000 microseconds. And if we want to convert that, let's see, that would be 0.01 seconds, 10,000 microseconds. Let me double check here. Yep, 0.01 seconds. That's our time value. 0.01 seconds. Where'd the rest of my work go? There we go. We have our negative sign. We have our 0.01 seconds. We have the negative 6.91. And that gives us a time value of 0.0691 seconds to reach 99.9% of the maximum charge that this capacitor can hold. And so all we have to do now is we have to ask ourselves, well, is 99.9% good enough? Is it close enough? And, you know, who knows? Depending on what it is that you're doing, maybe it's not close enough. Maybe you need to go to 99.99%. In that case, we would add an extra 9 to our work, which means we would have to add an extra 0 inside our decimal, and that means that instead of a negative 6.91, the natural log of 0.0001 is actually negative 9.2. And that's an increase of almost 50%, which means that we're going to see an increase in almost 50% of the required time just to add an extra 0.01%. Well, why did it take so long? And that's because your capacitor is almost at maximum charge. It's going to take quite a while for any new charges to make their way onto that capacitor plate, because that capacitor really doesn't want any more charge. It's going to take a long time to bring in that teeny tiny final percentage. But even still, if you're talking about less than 1/10 of a second between the two. This is something where if you hooked up the circuit, basically you snap your fingers and it's done. But there could be other circuits out there where the time constant is so high that you might have to get up and walk away for a while, go take a bathroom break, go to lunch, come back, and then the capacitor might be charged up fully. But that would require a much larger resistor, much larger capacitor in order for that to happen. This is what we call the charging scenario. We have charged up our capacitor. We started from 0 charge, we worked our way up to a maximum. We now see how we can solve for the time that is required to reach the maximum. We have these time-dependent functions that tell us how our capacitor is going to charge up in the circuit. And that means we are to the point where we now get to flip the switch. We're going to flip the switch down. In doing so, we have disconnected the battery from the circuit. So the battery, because the battery is no longer part of any closed loop, it may as well not even be in the diagram. The only thing that we have left now in our picture is the resistor and the capacitor. Once we flip that switch, what's going to happen? Well, the charges on the capacitor plates, they can't get to each other across this chasm here. But now that the switch has been flipped, there is a direct route in which positive charges and negative charges can come together and nullify. And so that's what's going to happen. We're not going to have this case scenario anymore. We're going to have a new circuit problem. And the only thing that we can really take with us is this value right here. Whatever charge that we were able to build up onto the capacitor plate before we flipped the switch, that is the charge that we now get to have on the capacitor for the next problem. And I'm going to scroll down in my work here. We have the resistor, the capacitor, and it was connected to a switch. All that positive charge that was on the capacitor plate, come on eraser, there we go. All that charge on the capacitor plate is now going to pass through the resistor and nullify with the charge on the opposite plate. The maximum charge that we had on the capacitor plate, we said that that was CE. Now that value does depend on the battery that our circuit was previously hooked up to. But this is now going to become the initial charge value that is on our capacitor. As time goes by, all of that charge should nullify, and we should get a final charge value of 0. If the final charge in the circuit becomes 0, that means there's no charge to move around, and so the final current in the circuit is going to be 0. But that just implies that the maximum current should occur at t equals 0 again. We're using the same resistor and capacitor as before, but the battery is no longer a part of this closed loop. That is going to change the Kirchoff's law description. Kirchoff's law says, pick a starting point. I'll pick this point right here. And we need to go around the closed loop, adding up all the potential differences. Well, there's only two things in this loop, the resistor and the capacitor. The switch doesn't count. The switch is just like a wire. It's just a way of connecting 2 points. But we can see that the positive charge is going to want to leave the positive plate and go down to where the negative charges are. So I'm going to say that this is where my current is flowing. And that's going to be time dependent, because as time goes by, the charge is going to nullify itself. But that means that as time goes by, the amount of charge on the capacitor is changing as well. So very similar picture, it's just that we don't have a battery. I will start at VB. I will choose to go around the circuit in the direction that the current is traveling. I pass through the resistor going with the current. That is a drop in potential. Then we come down to the capacitor, and to get across the capacitor, I have to emerge on the positive plate of the capacitor. Our equation for the potential of a capacitor is the ratio of charge to capacitance. Once I pass over the capacitor, I'm back to VB. VB's cancel out. Everything equals 0. Or, at any given time, the potential of the resistor has to be equal in magnitude, or rather equal and opposite, to that of the capacitor. That's the only way that we can get 0, by combining two terms. Now, I'm going to go ahead and rearrange this equation slightly. I'll bring the charge term over, set that equal to 0. And that's because we need to rewrite the current as a time-dependent function of Q. Current is the derivative of charge with respect to time. Once we combine that with the charge of the capacitor, we've produced another differential equation. And this differential equation will also need to be solved. We need to get a solution for this one, which, again, as you can probably tell, we're going to have another exponential function, because otherwise we can't combine these two terms as like terms. And we're gonna skip ahead to the solution. Again, this is better suited for a differential equations class. So we've got some more math magic here. We're going to jump ahead to the solution. The solution is that QT equals Q naught e to the negative t over RC. Well, what's this Q naught here? Well, that's the initial amount of charge that you had on your capacitor when you flipped the switch. And that has already been established for us. After we were done charging this capacitor and we flipped the switch, this was how much charge was on that capacitor. Now please note, this is the maximum charge. That does not necessarily mean that you have to have a capacitor that is maxed out on its charge. Maybe you charge the capacitor up to 50% of its maximum, and then you decide to flip the switch. If that's the case, then the initial charge that you start with would be 50% of the maximum, and that's what you would have to plug in down here. Now, again, if you're not quite sure, is this a solution to that equation? Well, plug it in. Plug in the function for Q, divide it by C. Then take the derivative of that function, multiply it by R, add it up, make sure you're getting 0, and you will. I'm going to skip that part because we already saw the solution for the charging capacitor case. We now have what we're going to call the discharging capacitor. Our capacitor is now going to be expelling that charge, or as we said, discharging. If this is the function for the charge at any given time, well, let's get a function for the current. For that, all I have to do is take the derivative, and if I take the derivative, I get Q naught. We have e to the AT, and A in this is equal to negative 1 over RC. And so this would be our current term. All right. So let's finish off by discussing those extremes. We said that there should be a maximum charge value of CE when time equals 0. Okay, well, if we let time equal 0, e to the 0 is 1, and so we're just left with Q naught. But that's what we set up here, was that the initial charge Q naught was going to be the maximum charge from when we flip the switch. But I'll reiterate there that initial charge does not always have to be the maximum. If we let this go for a really long time, eventually all the charge should nullify. So what happens if the time goes to infinity? Well, e to the negative infinity is 0, and so the whole thing goes to 0. And so that part checks out. For the currents, we should have a maximum current when time is 0. When time is 0, e to the 0 is 1, and we just have our initial charge over RC. The initial charge will be the maximum charge that we will ever have for this capacitor, because as time goes on, that charge is going to nullify during the discharge. If we let the time go for very long, if we let the time go to infinity, we were saying that the current should go to 0. So if we let t go to infinity, e to the negative infinity is 0, and so our current is 0. Now, just in case you were wondering, how long would it actually take for this capacitor to completely discharge? Well, we can do that. We can say that in order for the capacitor to completely discharge, we need to let the charge go to 0. And then we can attempt to solve for time, but I think you're going to see that after we divide out the initial charge value, we're going to end up taking the natural log of a 0, and that's going to give us an undefined time value. But we can pull the same trick that we did when we were charging the capacitor. We said let the capacitor charge up to 99.9% of its final value. Well, what if we let the capacitor discharge 99.9% of its initial value? In other words, we would be down to 0.001% of the initial charge. And that we can do. That we can apply a natural log to. The natural log and the exponential will eliminate each other. We will multiply over by a negative RC. And so the time to discharge this capacitor down to 0.1% of its original value. We plug that into our calculator. We can go back up and get the R and C values, but at this point I think we can realize that there are a lot of different resistor capacitor combinations that we could put into a circuit. We're going to close up this video and this chapter. I will leave you with one comment, and that is that it is possible that you could have a couple of resistors or capacitors in a circuit. And if that were the case, how would you handle it? If you had resistors 1 and 2 and capacitors 1 and 2, how would you handle that? If it were me, I would start by combining those two capacitors in parallel to make an equivalent capacitor, which I would name capacitor 1, 2. That capacitor would be connected in parallel with resistor 3, or resistor 2, sorry. We don't have a resistor 3. So what would happen in a circuit like this? Well, our battery would start by providing some current. But when that current gets to this intersection, some of the charge will travel to the capacitor and start filling up the capacitor plate. But some of the charge will pass through resistor 2. Whatever this incoming charge is going to have to equal the currents that split to go to resistor 2 and to the capacitor. But as time goes by, the current on the capacitor, or better yet, we should say that the charge on the capacitor is going to build up until we achieve a maximum. And then there's not going to be any more current going to that capacitor. So where does all the total current from the battery go? Well, it has to go through resistor 2. This is a case of what we would call equilibrium or steady state. We would introduce charge to the circuit until the capacitor is full, but as the capacitor fills, current 2 will consistently get larger and larger because less and less charge can be deposited on the capacitor as time goes by. So how would you represent this? Well, Kirchoff's law. You have two distinct loops within this circuit that you can set up Kirchoff's law. Or if you prefer, there's even a third loop that you could use. We can use the first loop, which involves the battery and the two resistors. There is the second loop that involves the combined capacitors and resistor 2. Or you have the outer loop that you can use. Then, if you feel so inclined, you can backtrack in your work. You can split that equivalent capacitor back up into capacitors 1 and 2 and you can find the potential difference and charge values for each of those capacitors using the information that we know about equivalent capacitance. So all of this stuff just kind of came together all at once. I realize that it might look a bit overwhelming, but I'll put your anxieties to rest. We're not going to focus a whole lot on the RC circuits. If you do need to deal with RC circuits, I'm guessing that you're probably a computer engineer or electrical engineer, and you're going to have dedicated coursework that will take you beyond what we've discussed today. But for right now, I would expect that you be able to use the equations that have been produced in these discussions, and you do need to be able to recognize the difference between charging a capacitor and discharging a capacitor, because you have different sets of equations. And it is crucial that we grab the correct equations from our formula sheet when we go to take a test. So down here, these are the discharge equations, and the ones up above are for the charging scenario. And with that, we bring ourselves not only to the end of Chapter 27, but also to the end of the circuits portion for this course. In Chapter 28, we will begin our discussions on magnetism, magnetic fields, magnetic forces. And so a lot of the stuff that we cover in these last 3 chapters is very closely going to mirror what we saw in the first 3 chapters of the electric charge, electric field discussions. And so we're going to look at how electric charges relate to magnetic fields, how magnetic fields can be derived, how magnetic forces are going to work, and then we will apply that information back to circuits. So, see you back for Chapter 28.